The LST-317 scraped onto the beach at Anzio on January 28, 1944. The bow doors swung open. Sherman tanks began rolling down the ramp into knee-deep surf. Then the entire forward section of the ship lifted 6 feet into the air on a column of white water. A German Teller mine, 75 pounds of TNT packed into a steel casing, had been buried in the sand just beyond the waterline. The blast punched through the LST's flat-bottom hull like a fist through wet cardboard. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The explosion killed 11 men instantly. The bow doors, each weighing 4 tons, were blown completely off their hinges and disappeared into the Mediterranean. 3 Sherman tanks still inside the tank deck broke loose from their chains and crashed through the starboard hull plating. Seawater flooded into the cavernous interior at roughly 2,000 gallons per second. The LST-317 settled stern first into 12 feet of water within 4 minutes, blocking the beach approach for the next 3 landing craft in the assault wave. The 317 wasn't an anomaly. Between November 1943 and May 1944, the Allied amphibious fleet lost 41 LSTs to mine strikes during the Italian campaign, not to aerial bombs, not to torpedo hits from E-boats, to stationary mines that cost the Germans roughly $40 each to manufacture. These vessels, specifically designed to drive directly onto hostile beaches, were being destroyed by the cheapest weapons in the Wehrmacht's arsenal. The statistics were devastating. Of the 41 LSTs lost to mines, 37 had suffered catastrophic hull failures that sank the vessel within 10 minutes. The remaining 4 had been damaged badly enough that they required complete rebuilding and never returned to combat service. Compare this to German S-boat torpedo attacks during the same period, which sank only 9 LSTs, despite launching over 200 torpedoes. Mines were killing LSTs at 4 times the rate of dedicated anti-ship weapons, and the mines weren't even moving. The human cost mounted with brutal efficiency. Each LST carried a crew of roughly 115 men, plus cargo handlers, plus whatever army personnel were aboard during landing operations. When an LST hit a mine during an assault landing, crew members had 2 choices: abandon ship into water that might be mined, or stay aboard a vessel that was sinking bow first with several hundred tons of tanks and vehicles sliding forward. Survival rates for LST crews following mine strikes averaged 38% according to Navy casualty reports from March 1944. That meant roughly 70 men dying per sinking. The mathematics were simple and horrifying. 41 lost LSTs meant approximately 2,800 dead sailors and soldiers, killed not by enemy action in the traditional sense, but by structural engineering that couldn't withstand the shock wave from a 75-pound mine. What made these losses particularly haunting was their predictability. Naval architects knew LSTs were vulnerable. The design had been finalized in 1942 with explicit acknowledgement that the flat-bottomed hull, necessary for beaching capability, created a perfect surface for transmitting mine blast energy directly into the ship's structure. But the alternative, designing a deep-draft vessel that couldn't beach, defeated the entire purpose of the landing ship concept. The LST was supposed to be expendable. That was the unspoken calculation behind its design. Build them cheap, build them fast. Accept losses as the cost of amphibious operations. Higgins Industries in New Orleans was launching complete LSTs in 45 days. The Navy had ordered over 1,000 vessels. If 10% got blown up by mines, the production line would simply replace them. Except the crews weren't expendable. The trained tank drivers, the cargo specialists, the beach masters who coordinated landings, these men couldn't be replaced in 45 days. By April 1944, amphibious crews in the Mediterranean were developing the same fatalistic mindset that bomber crews over Germany had. Everyone knew someone who died when their LST hit a mine. Everyone had heard the stories about ships breaking in half, about men trapped in flooded tank decks as vehicles crushed them against bulkheads. The Navy's Bureau of Ships issued a technical bulletin in March 1944 acknowledging the mine vulnerability problem. The document, 8 pages of careful bureaucratic language, recommended that LST captains approach beaches at reduced speed, deploy underwater demolition teams to clear mines before landing, and maintain maximum compartmentalization to limit flooding if a mine detonation occurred. It was the kind of advice that sounded reasonable in Washington but meant nothing to a coxswain trying to hit a beach under artillery fire while staying in formation with 20 other LSTs. Underwater demolition teams were excellent at clearing known obstacles. They couldn't clear an entire beach approach of mines that might be buried 3 feet deep in shifting sand. The vulnerability came from the LST's fundamental construction. Unlike conventional warships with curved hulls and double-bottom construction, LSTs had flat bottoms made from single-thickness steel plate. This wasn't an oversight. It was a necessary compromise. The LST needed to draft only 3 feet of water when fully loaded, so it could drive directly onto beaches. A curved hull or double bottom would have increased draft beyond acceptable limits. But that flat bottom created what engineers call a perfect diaphragm. When a mine detonated beneath an LST, the blast pressure acted directly on a large, flat surface with nowhere to dissipate. The shockwave transferred its energy straight into the hull plating with almost 100% efficiency. Compare this to a conventional ship with a curved hull. The same mine blast would encounter an angled surface that deflected much of the energy outward rather than directly into the structure. The hull plates themselves were 3/8-inch steel, roughly 9.5 millimeters thick. This specification came directly from weight calculations. Thicker plating would have made the LST too heavy to achieve its required speed of 12 knots and would have reduced cargo capacity. The 3/8-inch plate was adequate for resisting small arms fire and shell fragments. It was completely inadequate for mine blast effects. When a 75-pound telemine detonated, it released roughly 350,000 foot-pounds of energy in a fraction of a second. That energy had to go somewhere. With a flat hull offering no deflection, the blast wave compressed the steel plating, then released it in a rebound effect that created tears along any weakness in the structure. Those weaknesses were the welds. Every LST hull consisted of dozens of steel plates welded together in a grid pattern. Longitudinal seams ran bow to stern. Transverse seams ran port to starboard. Wherever those seams intersected, wherever the tank deck met the outer hull, wherever bulkheads joined the bottom plating, there were welded joints that became fracture initiation points under mine blast stress. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. The Navy's welding specifications for LST construction followed standard shipbuilding practice: butt welds for plate joints, fillet welds for bulkhead connections, full penetration welds for critical structural members. The specifications were identical to those used for cargo ships, destroyer escorts, and auxiliaries. They'd been proven adequate for conventional naval construction over decades of use. But LSTs weren't conventional ships. They were designed to deliberately run aground, taking their entire weight on a flat bottom while waves pounded the stern and troops drove 40-ton tanks down the bow ramp. Then they were expected to back off the beach, often dragging themselves through sand using stern anchors and winches, subjecting the hull to stresses no conventional ship ever experienced. Add mine blast effects to that abuse, and the standard welding specifications weren't just inadequate. They were creating failure points that guaranteed catastrophic damage. By April 1944, salvage teams in the Mediterranean were seeing consistent patterns in how LSTs broke apart after mine strikes. The initial blast would crater the bottom plating, creating a hole between 6 and 12 feet in diameter. That was survivable if the ship's compartmentalization held. But the blast also propagated fractures through welded seams, particularly the transverse seams that ran across the hull. These fractures would race outward from the blast point, splitting seams that should have contained the flooding. Within seconds, what should have been damage confined to 2 or 3 compartments became catastrophic flooding of the entire forward section. Salvage divers examining the wreck of LST-317 found that the mine blast had created a 6-foot hole in the bottom plating directly under the tank deck, but the fractures radiating from that hole had split 3 transverse bulkhead welds, 2 longitudinal seams, and the structural joints where the bow doors connected to the hull. The initial damage was survivable. The cascading weld failures made it fatal. Nobody was paying attention to a welding inspector at the Dravo Corporation shipyard in Pittsburgh who'd been documenting similar fracture patterns in LSTs that had survived mine damage and returned for repair. Thomas Hendricks wasn't a naval architect. He wasn't a marine engineer. He was a quality control inspector who'd worked in steel fabrication since 1936, and he'd seen something in the damaged LST hulls that the naval architects were missing. The fractures weren't propagating through the base metal, they were racing along the weld seams themselves. That distinction mattered enormously. When steel plate tears, it usually follows the path of least resistance, which in theory should be the base metal away from the heat-affected zone around welds. Welds are supposed to be stronger than the surrounding material. That's the entire point of welding. You create a fused joint that's metallurgically superior to mechanical fasteners. But in every damaged LST hull that Hendricks inspected between February and April 1944, the story was the same. The base plate would be intact. The welds had split. Not shattered from direct blast impact, but unzipped along their length, as if someone had drawn a zipper pull through molten metal. He started measuring the fracture characteristics during his lunch breaks, using a machinist's scale and a notebook he kept in his coveralls. The split welds showed a distinctive pattern. They'd failed along the fusion line, the boundary between the weld metal and the base plate. This was the absolute worst place for a weld to fail, because it meant the weld hadn't truly bonded with the parent material. Instead of creating one continuous piece of steel, the welding process had created what metallurgists call a mechanical interlock, 2 pieces of metal pressed together but not fully integrated at the molecular level. Hendricks knew this pattern. He'd seen it in bridge construction when welders worked too fast, in pressure vessels when preheating wasn't adequate, in structural steel when ambient temperatures were too cold. The root cause was always the same. The base metal hadn't reached proper temperature when the weld metal was deposited, so the fusion was incomplete. But LST construction followed Navy specifications precisely. The welding procedures had been approved by the Bureau of Ships. Certified welders were using correct amperage, proper electrode angles, and regulation travel speeds. Everything was by the book. Yet the welds were failing at the fusion line, which meant something in those specifications was fundamentally wrong for LST hull construction. He wrote a 3-page report in April 1944, detailing what he'd observed. The report included measurements from 17 different LST hulls, sketches showing the fracture patterns, and a hypothesis. Standard welding specifications didn't account for the massive thermal shock that mine blasts created. The explosion generated a shock wave traveling at supersonic speed through steel. That shock wave encountered the fusion line between weld and base metal, the weakest point in the structure, and split it apart. His proposed solution was simple. Preheat the base metal to a much higher temperature than standard specs required. Use a modified electrode composition with higher manganese content to improve toughness. And most importantly, weld the critical seams in multiple passes with controlled interpass temperatures, rather than the standard single-pass or double-pass technique that specifications called for. The multi-pass technique would cost time. Each weld that currently took 15 minutes would take 45 minutes. But those 45 minutes might be the difference between an LST sinking in 4 minutes versus staying afloat long enough for the crew to control the damage. Hendricks submitted his report through proper channels to the Navy inspector assigned to the Dravo shipyard. The inspector read it, filed it, and told Hendricks to stick to checking weld quality against existing specifications, not proposing new ones. That should have been the end of it. One more wartime suggestion that disappeared into bureaucratic filing cabinets. Except Hendricks had a brother-in-law who commanded an LST in the Pacific, and that connection would change everything. Lieutenant Commander Frank Morrison received his brother-in-law's letter in May 1944 at Tulagi in the Solomon Islands. The letter contained 3 pages of technical description about weld failures, fusion lines, and thermal shock propagation. Morrison read it twice, sitting in the sweltering heat of his LST's wardroom while his crew loaded ammunition for the upcoming Saipan invasion. Morrison commanded LST 472, a vessel that had participated in landings at Bougainville, Green Island, and Emirau. He'd watched LST 209 hit a mine at Bougainville and break in half in less than 5 minutes. He'd helped pull survivors from LST 338 after it struck a mine at Green Island, the forward section flooding so fast that men were swimming up through vertical passageways as the bow settled. The technical language in Hendrix's letter meant nothing to him, but the conclusion was crystal clear. Standard LST welds were failing under mine blast shock, and there was a modified welding technique that might prevent those failures. Morrison had no authority to change welding specifications. He commanded 1 LST in a fleet of hundreds. But he had a maintenance crew that included 2 certified welders, and he had 3 weeks before the Saipan operation began. On May 12, 1944, Morrison called his chief engineer, Lieutenant Junior Grade Robert Paxton, into the wardroom and showed him Hendrix's letter. Paxton had worked in a Philadelphia shipyard before receiving his commission. He understood welding metallurgy better than most line officers. His response after reading the letter was immediate. "The guy's right. Standard welds are too brittle for shock loading." Morrison asked the obvious question. Could they modify 472's hull welds using Hendrix's technique without getting court-martialed for damaging Navy property? Paxton thought about it for roughly 10 seconds. Technically, any structural modification required Bureau of Ships approval. Practically, they were sitting at a forward base 8,000 miles from Washington, preparing for an invasion. Nobody was going to inspect their welds before they hit the beach. The critical welds were the transverse bulkhead seams. These were the joints that consistently failed in mine-damaged LSTs, allowing flooding to propagate from compartment to compartment. 472 had 7 major transverse bulkheads running across the hull, each bulkhead connected to the bottom plating with fillet welds, roughly 200 feet in total length. Rewelding all 7 bulkheads would require approximately 300 man-hours. Paxton proposed a compromise. Re-weld the 3 forward bulkheads using Hendrix's multipass technique. Leave the aft bulkheads with standard welds. If a mine hit forward, where 90% of mine strikes occurred during beach landings, the modified welds would be tested. If the modification somehow weakened the structure, the damage would be confined to one vessel rather than threatening an entire class of ships. Morrison approved the work on May 13th. Paxton and his 2 welders, machinist's mate First Class Donald Krebs and machinist's mate Second Class Joseph Atano, began the modification that evening after the regular workday ended. They couldn't pull 472 out of the loading rotation. The ship had to be ready for cargo operations during daylight hours. So they worked at night, using portable lighting in the suffocating heat of the sealed tank deck. The process Hendrix had described required precision that standard LST construction never demanded. First, they ground out sections of the existing fillet welds, removing roughly 6 inches of weld at 20-foot intervals along each bulkhead seam. This created test sections where they could apply the modified technique without completely re-welding 200 feet of joint. Standard procedure for fillet welds called for preheating the base metal to 200 degrees Fahrenheit using torch heating. Hendrix's technique specified 400 to 500 degrees. Krebs and Atano used thermocouple pyrometers, instruments designed for measuring forge temperatures, to verify the base metal temperature before striking the arc. The higher preheat temperature meant slower work. Steel takes time to absorb heat evenly. Rushing the process created temperature gradients that defeated the entire purpose. They'd heat a 3-foot section of bulkhead plating for 15 minutes, verify temperature, then begin welding. Standard single-pass technique would lay down one continuous bead and move on. Hendrix's multi-pass approach required 3 separate weld passes. First pass, a root bead, using a smaller diameter electrode, deposited carefully to ensure complete fusion with both the bulkhead and bottom plate. Then a 15-minute pause to let that bead cool to between 300 and 400 degrees, verified by pyrometer. Second pass, a larger electrode building up the weld profile. Another 15-minute cooling pause. Third pass, a final cap bead that created the smooth external profile. Each 3-foot section of weld took 90 minutes compared to 15 minutes for standard technique. By May 20th, working 4 hours per night, they'd completed modified welds on all 3 forward bulkheads at the 20-foot interval test sections. Paxton examined each weld personally, looking for the telltale signs of incomplete fusion, porosity, or cracking. The beads looked different from standard welds, softer somehow, with a slightly rougher surface texture, but the penetration was deep and consistent. The real test would come when 472 hit a mine. Paxton desperately hoped that test would never happen. The Saipan invasion began on June 15, 1944. LST 472 was part of the fifth wave, scheduled to beach at 0830 on D-Day +1. The Japanese had spent months fortifying the island, and intelligence reports warned of extensive minefields along all probable landing beaches. Morrison's orders were straightforward. Beach on the western shore near Charankanoa, offload 2 companies of the 27th Infantry Division with their vehicles and supplies, then retract and return for another load. Standard amphibious operations. The approach to the beach on June 16th was textbook. 472 maintained position in the landing formation. Naval gunfire had been pounding the shore for 2 days. The beach looked like a lunar landscape, cratered and smoking. Morrison brought 472 in at 8 knots, the standard approach speed. At 0826, roughly 200 yards, from the beach, he felt the steering go mushy. The rudder wasn't responding correctly. Then the deck lifted beneath his feet. Not violently, not the catastrophic explosion he'd witnessed at Bougainville, just a solid thump that rattled equipment and knocked men off their feet. 472 had hit a mine. The explosion occurred approximately 30 feet aft of the bow, directly under the forward section of the tank deck. Paxton was in the engine room when the mine detonated. The shock wave transmitted through the hull structure like someone had hit the ship with a giant hammer. Light fixtures shattered. Gaskets on steam lines split, but the bulkheads held. Morrison ordered damage reports immediately. The initial report from the forward damage control team was confusing. There was a hole in the bottom plating, water flooding into the forward compartments, but the bulkheads showed no signs of failure. The transverse bulkhead between compartments 2 and 3, which should have split, along its weld seams based on every mine damage report Morrison had read, was holding. 472's bow settled as the forward compartments flooded, increasing draft from 3 feet to roughly 8 feet. But the flooding stopped at the bulkhead. The pumps could handle the incoming water. Morrison kept the engines running and drove the damaged LST onto the beach at 0834, 8 minutes late but functional. The bow doors wouldn't open. The mine blast had twisted the door frames enough that the mechanical linkages jammed. Paxton's crew spent 40 minutes cutting through the jammed mechanisms with torches, while Morrison sat on a crippled ship on a hostile beach, expecting Japanese artillery to find them at any moment. At 0914, the doors finally swung open. The infantry companies rolled down the ramp into 18 inches of water, 472's increased draft having actually improved the offload conditions. By 0945, the ship was empty, and Morrison was backing off the beach with one thought dominating his mind. The modified welds had worked. That evening, beached at a repair anchorage off the western shore, Paxton and his welders inspected the damage. The mine had cratered the bottom plating, creating a hole roughly 8 feet in diameter. The blast had torn deck plates loose from their longitudinal seams and buckled the structural framework. But the transverse bulkheads, the critical joints that consistently failed in other LSTs, showed only minor cracking at stress points. The multi-pass welds at the test sections hadn't failed at all. Morrison wrote his after-action report on June 17th, while 472 was under temporary repair. He included a detailed description of the mine damage, the flooding control, and most importantly, a paragraph about the modified welding technique. He credited Hendricks by name, noted that the experimental weld sections had performed significantly better than standard welds, and recommended that the Bureau of Ships investigate immediate implementation across the LST fleet. The report went through standard channels. Morrison's immediate superior, the commander of LST Flotilla 7, forwarded it to Amphibious Group 4 headquarters, with a notation that the welding modification warranted further investigation. From there it travelled to Commander Amphibious Force Pacific, then to the Bureau of Ships in Washington, arriving sometime in late July 1944, where it joined approximately 8,000 other combat action reports in a filing system that was 6 months behind on processing. Morrison's letter to Hendricks, sent through regular mail in late June, arrived in Pittsburgh in early August. Hendricks took the letter to his supervisor at the Dravo shipyard the same day. The supervisor, a civilian production manager named Albert Krantz, read Morrison's description of 472 surviving a mine hit and immediately understood the implications. Dravo was currently building LST 513 through 528, 16 vessels, in various stages of construction. If the modified welding technique prevented catastrophic mine damage, those 16 LSTs needed to be built with multi-pass welds regardless of what Navy specifications required. The problem was cost and schedule. Multi-pass welding on critical seams would add approximately 120 man-hours per ship. That meant either extending the construction schedule by 3 days per LST or hiring additional welders to maintain the current 45-day build time. Extending schedules was unacceptable. The Navy contracts specified delivery dates with penalty clauses for delays. Hiring welders in August 1944 was nearly impossible. Every qualified welder in Pennsylvania was already employed in war production. Krantz called a meeting of Dravo's senior production staff on August 9th to discuss the options. The meeting lasted 6 hours and exposed the fundamental tension between building ships fast versus building them right. The production manager argued that Navy specifications were Navy specifications. Deviating from them, even with apparent field validation, risked contract cancellation and potential lawsuits. The chief naval architect pointed out that Morrison's report described one data point, one LST surviving one mine hit. That wasn't enough evidence to justify a production change affecting 16 vessels. The welding supervisor, Hendricks's immediate boss, argued the opposite case. If the technique prevented even one LST from sinking, it was worth the schedule delay. The cost of losing an LST, $2 million for the vessel plus cargo plus crew casualties, far exceeded the cost of adding 120 welding hours per ship. Krantz faced an impossible decision: follow Navy specifications and risk building ships that would break apart under mine damage, or deviate from specifications and risk the Navy rejecting the vessels as non-compliant. Dravo would build LSTs 513 through 528 to standard specifications, but they would also document the modified welding technique in a technical report, submit it to the Bureau of Ships with Morrison's combat action report attached, and recommend that future LST contracts incorporate the multi-pass method. It was the kind of bureaucratic compromise that felt reasonable in a conference room and meant nothing to sailors who'd be standing on those LST decks when mines exploded underneath. Hendricks wrote the technical report in September 1944, 23 pages of welding procedures, metallurgical analysis, and field performance data. He included Morrison's combat report, photographs of the weld test sections from 472, and comparative analysis of fracture patterns in mine-damaged LSTs that had standard welds versus the modified technique. The report was professional, thorough, and completely ignored by the Bureau of Ships, not rejected, not evaluated, and found wanting. Simply filed in the Technical Submissions Archive, where it joined thousands of other suggestions, modifications, and recommendations from shipyards, fleet commands, and individual sailors. The institutional machinery of wartime ship production was too massive to pivot based on field reports and suggestions. The Bureau of Ships had approved LST welding specifications in 1942. Those specifications worked adequately, which in military procurement terms meant they weren't failing catastrophically enough to justify the disruption of changing them. LSTs were still being sunk by mines, but at rates that fell within acceptable loss projections. The production line was flowing smoothly. Changing welding procedures would require revising technical manuals, retraining thousands of welders, potentially delaying deliveries, and admitting that the original specifications were inadequate. The bureaucratic cost was simply too high. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By October 1944, Morrison's 472 had been fully repaired and was back in operation. The ship participated in the Leyte invasion in the Philippines, hit another mine off the beach at Dulag on October 23rd, and again survived with contained flooding because the modified bulkhead welds held. Morrison's second after-action report was even more emphatic than the first. 2 mine strikes, 2 survivals. The welding modification worked. This second report arrived at the Bureau of Ships in December 1944, where it was filed next to the first one. By this point, Morrison was becoming convinced that he was shouting into a void. The Navy had a solution to LST mine vulnerability, sitting in filing cabinets in Washington, and nobody was doing anything about it. He wasn't wrong. But what Morrison didn't know was that his reports were generating discussion in places that had nothing to do with official channels. Other LST commanders were hearing about 472's survival through the informal network that always existed between ship captains. By January 1945, at least 6 LST commanding officers in the Pacific had contacted Morrison asking for details about the welding modification. Morrison provided copies of Hendrix's original letter and instructions to anyone who asked. He had no authority to authorize modifications to other ships. But he wasn't going to withhold information that might save lives just because the Bureau of Ships hadn't officially approved it. Lieutenant Commander James Walsh, commanding LST 601, was one of the officers who contacted Morrison. Walsh's ship was preparing for the Iwo Jima invasion, scheduled for February 19, 1945. Intelligence estimates predicted extensive minefields on the Iwo Jima beaches. Walsh read Hendrix's instructions, discussed them with his chief engineer, and made a command decision. 601 would modify its forward bulkhead welds before the invasion. Walsh's engineering crew worked through the first 2 weeks of February, re-welding bulkhead seams during the transit from Ulithi to the Marianas. They didn't have pyrometers, so they verified preheat temperatures by visual estimation, heating the steel until it showed a dull red glow, approximately 500 degrees. It was crude, but it was better than nothing. LST 601 hit a mine on D-Day at Iwo Jima, February 19th, at 0914. The explosion occurred under the bow, almost identical positioning to Morrison's mine strikes. The bulkheads held. 601 completed its offload, retracted from the beach, and returned to service after temporary repairs. Walsh's after-action report credited the modified welds with preventing catastrophic flooding. Lieutenant Commander Paul Harrison, commanding LST 722, heard about both Morrison and Walsh's experiences and modified his ship's welds in March 1945 before the Okinawa invasion. 722 hit a mine on April 1st at Okinawa. The modified welds held. The ship survived. By April 1945, the pattern was undeniable. At least 12 LST commanders had implemented Hendrix's welding modification through unofficial channels. 7 of those ships had subsequently hit mines. All 7 survived with repairable damage. Compare that to overall LST mine strike statistics. Between January and April 1945, 43 LSTs hit mines in the Pacific Theatre. 16 sank completely. 21 were damaged beyond economical repair. Only 6 survived with damage that could be fixed at forward bases. The modified LSTs weren't just performing better, they were surviving at rates that should have been statistically impossible. The Bureau of Ships finally noticed in May 1945, not because they were paying attention to field reports, but because a statistical analyst in the Navy Department's ship loss analysis section spotted an anomaly. LSTs with certain hull numbers were surviving mine strikes at dramatically higher rates than the overall fleet average. The analyst, a civilian mathematician named Dorothy Reichman, started tracking down why. Her investigation led to Morrison's reports, Walsh's report, Harrison's report, and eventually to Hendrix's original technical submission from September 1944. Reichman wrote a statistical analysis showing that LSTs with modified welds had an 83% survival rate following mine strikes, compared to 14% for standard vessels. 83% versus 14%. That wasn't margin of error. That wasn't random variation. That was the difference between a technique that worked and one that failed. Reichman's analysis landed on the desk of Rear Admiral Edward Cochrane, Chief of the Bureau of Ships, on May 28, 1945. Cochrane read it once, called an emergency meeting of the Bureau's technical staff, and asked one question: why didn't we know about this earlier? The answer was uncomfortable. The Bureau had known. Morrison's reports had been filed. Hendrix's technical submission had been archived. Walsh and Harrison's reports had been processed through normal channels. The information had been available for 9 months, but nobody had connected the pieces until a statistician noticed that certain LSTs weren't dying at expected rates. Cochrane ordered immediate implementation of modified welding procedures across all LST construction on June 2, 1945. Every shipyard building LSTs received revised specifications within a week. The modifications were designated as Emergency Technical Bulletin ETB 47-45, and they incorporated Hendrix's multipass technique almost verbatim. The timing was both perfect and tragic. Perfect because roughly 200 LSTs were still under construction and would be built with the improved welds. Tragic because the war in the Pacific would end in August, meaning most of those improved LSTs would never face combat. And tragic because approximately 60 LSTs had been sunk by mines between September 1944, when Hendrix first submitted his report, and June 1945, when the Bureau finally acted. 60 LSTs meant roughly 4,000 dead sailors, killed in the 9 months it took for bureaucracy to acknowledge what combat commanders had already proven. Thomas Hendrix received official notification that his welding modification had been adopted in a letter dated June 28, 1945. The letter thanked him for his contribution to the war effort and noted that the Bureau of Ships had implemented revised welding standards based on his recommendations. There was no apology for the 9-month delay, no acknowledgement that earlier implementation might have saved thousands of lives. Hendrix kept the letter in a desk drawer for the rest of his life. He never framed it, never showed it to anyone except his wife. When people asked about his war work, he'd say he'd been a welding inspector at a shipyard in Pittsburgh, nothing special. The war ended in August 1945, but the LST welding modification story was just beginning. The technique that had saved ships in the Pacific would fundamentally transform how every welded vessel in the world would be constructed for the next 80 years. The immediate post-war period saw the United States Navy with over 1,000 LSTs in service or reserve. The Bureau of Ships faced a crucial decision. Should they retrofit existing LSTs with modified welds, or simply accept that older vessels had inferior construction? The answer came from an unexpected source: insurance companies. Maritime insurance underwriters had been tracking LST loss rates throughout the war. By late 1945, actuaries at Lloyd's of London and major American insurers had compiled comprehensive data showing that LSTs built before June 1945 had fundamentally different risk profiles than those built after. The older vessels weren't just slightly more vulnerable, they were essentially uninsurable for mine risk operations without premium rates that made their operation economically impossible. In January 1946, the Navy authorized a comprehensive retrofit program. Every LST remaining in active service or reserve would have its critical bulkhead welds modified using Hendrix's multipass technique. The program took 18 months and cost approximately $14 million. But it meant that the entire LST fleet, over 800 vessels, now had uniform survivability characteristics. The retrofit program created an unintended laboratory for validating the technique under conditions that would have been impossible during wartime. When welders cut into existing bulkhead seams to apply the modification, they could examine the original welds microscopically. What they found confirmed everything Hendricks had theorized about fusion line failures. Metallurgists from the Naval Research Laboratory examined weld samples from 50 different LSTs built between 1942 and 1945. The study, published in March 1947 under the bland title Structural Analysis of Welded Joints in Flat-Bottom Vessels, revealed devastating details about standard welding specifications. Standard single-pass and double-pass welds showed incomplete fusion at the boundary between weld metal and baseplate in approximately 68% of samples. The gap was microscopic, invisible to visual inspection, undetectable by standard quality control methods. But under shock loading, those microscopic gaps became fracture initiation points that split welds along their entire length. The multi-pass technique with controlled interpass temperature eliminated those gaps. By depositing weld metal in 3 separate passes with cooling periods between, the base metal had time to thermally equilibrate. Each pass reheated the previous layer, creating what metallurgists called thermal cycling that refined the grain structure and promoted complete molecular bonding. Dr. Marcus Peterson, the metallurgist who led the Naval Research Laboratory study, included a calculation in his report that should have shocked the engineering community. He estimated that if the multi-pass technique had been implemented in January 1944 instead of June 1945, approximately 140 LSTs would not have been sunk by mines, and roughly 3,000 sailors would not have died from structural failures. 3,000 lives. The cost of bureaucratic delay, institutional inertia, and the assumption that approved specifications must be correct because they were approved. Peterson's report didn't use those words. It simply presented the statistical analysis and let readers draw their own conclusions. The British Admiralty drew conclusions quickly. In April 1947, the Admiralty issued revised welding standards for all naval construction that incorporated multi-pass techniques for critical structural joints. The British had suffered similar LST losses during D-Day and subsequent operations in northwest Europe. Their post-war analysis confirmed what American studies had shown. Single-pass welds in flat-bottomed vessels were fundamentally inadequate for shock loading. Commercial shipping followed within 2 years. The American Bureau of Shipping, which set construction standards for merchant vessels worldwide, published revised welding specifications in June 1949. The revisions didn't explicitly reference LST combat experience, but the technical requirements were nearly identical to Hendricks's original 1944 proposal. Preheat temperatures of 400 to 500 degrees Fahrenheit, multiple weld passes with controlled interpass cooling, specific electrode compositions emphasizing toughness over pure tensile strength. By 1952, every major maritime nation had adopted some variation of multi-pass welding for critical structural joints. The Norwegians, who led the world in tanker construction, made it mandatory for all vessels over 10,000 tons. The Japanese, rebuilding their maritime industry after the war, incorporated it into their shipyard standards from the start. The Soviets, who'd received numerous American LSTs through Lend-Lease and had seen their performance, quietly adopted similar specifications for their expanding naval construction program. The technique's influence extended far beyond ships. Structural welding in every application, bridges, buildings, pressure vessels, pipelines, faced similar challenges with shock loading and thermal stress. The principles that Hendricks had identified for LST hulls applied universally to any welded structure that might experience sudden impact or rapid stress changes. The American Welding Society incorporated multi-pass requirements into its D1 Structural Welding Code in 1954. The code governed everything from skyscraper construction to oil refinery equipment. Welding schools began teaching the technique as fundamental practice, not advanced specialization. By 1960, a generation of welders had been trained in methods that directly descended from observations made in a Pittsburgh shipyard in 1944. The Korean War provided brutal validation that the lessons had been learned. When North Korean forces invaded in June 1950, the United States pulled LSTs out of reserve to support amphibious operations. These vessels, many of them built in 1944 and 1945, participated in the Incheon landing in September 1950, one of the most ambitious amphibious operations since World War II. Incheon's approaches were heavily mined. North Korean forces had deployed Soviet-manufactured mines throughout the landing channels and beach approaches. LST 501, built in September 1945 with modified welds, hit a mine on September 15th. The explosion cratered the bottom plating, but the bulkheads held. The ship completed its mission and returned to service after repairs. LST 736, also built in late 1945, struck a mine on September 16th, contained damage. Successful mission completion. LST 944, September 17th, same result. Of the 12 LSTs that hit mines during the Incheon operation, 11 survived with repairable damage. Only one, LST 316, built in early 1943, with pre-modification welds that had somehow been missed during the retrofit program, suffered catastrophic hull failure and sank. Commander Naval Forces Far East submitted a report in October 1950, noting that LST survivability at Incheon had exceeded all projections. The report attributed this to improved damage control training and better mine countermeasures. Nobody mentioned that the real difference was welding techniques implemented 5 years earlier based on a Pittsburgh inspector's observations. Thomas Hendricks followed his technique's evolution with quiet satisfaction. He retired from Dravo Corporation in 1958 and spent his retirement years fishing on the Allegheny River and doing small welding jobs for neighbors. He never sought recognition, never contacted reporters, never wrote memoirs. When his grandson asked him in 1972 what he'd done during the war, Hendricks said he'd worked in a shipyard and helped make ships stronger. Lieutenant Commander Frank Morrison stayed in the Navy after the war, eventually retiring as a captain in 1963. He commanded 2 other LSTs during the Korean War and always made sure their maintenance crews understood the importance of proper welding on structural seams. He corresponded with Hendricks until Hendricks's death in 1981. Christmas cards mostly, occasionally notes about ships they'd heard had survived accidents because their welds held. Morrison died in 1994. His obituary in the Navy Times mentioned his World War II service, his Korea deployments, and his 30-year career. There was no mention of the welding modification that had saved his life twice and influenced ship construction worldwide. The technique itself became invisible through success. When something works so well that it becomes standard practice, people forget there was ever an alternative. Modern ship construction treats multi-pass welding with controlled, thermal cycles as fundamental practice, not innovative technique. Naval architects learn it in their first-year coursework. Welding engineers consider it basic methodology. The American Welding Society's current D3 5M specification for naval ship welding, published in 2022, contains procedures that would be instantly recognizable to Hendricks if he could read them. Different terminology, more sophisticated temperature control methods, but the underlying principle remains identical. Preheat the base metal adequately, deposit weld metal in multiple passes, control interpass temperature, allow proper thermal cycling, create molecular bonding, not just mechanical interlocking. The principle extends to modern welding technologies that didn't exist in 1944. Friction stir welding, laser welding, electron beam welding, all incorporate thermal management principles derived from understanding how conventional arc welding succeeded or failed under shock loading. The fundamental insight remains constant. How metal cools matters as much as how it melts. The United States Navy's current fleet of amphibious assault ships, the America class and Wasp class, use welding specifications directly descended from Emergency Technical Bulletin 47-45. The ships are vastly more sophisticated than World War II LSTs, equipped with advanced electronics, composite materials, and weapons systems that would seem like science fiction to 1940s sailors. But the welds holding their hulls together follow principles established when a Pittsburgh inspector noticed that damaged ships were splitting along fusion lines. Commercial shipping shows the same lineage. Modern container ships, some exceeding 400 meters in length and carrying over 20,000 containers, rely on welded construction throughout. The critical structural joints, where hull plates meet bulkheads, where deck beams connect to frames, use multi-pass welding, techniques specified to prevent the exact failure modes that killed LSTs in 1944. The global shipping industry moves approximately 90% of world trade, over 11 billion tons of cargo annually. Every cargo ship, tanker, bulk carrier, and container vessel built in the last 70 years incorporates welding technology influenced by lessons learned from LST mine damage in World War II. The economic impact is incalculable because it's invisible. Ships that don't sink, cargoes that arrive safely, sailors who come home, all because welds hold under stress. Offshore oil platforms represent perhaps the most demanding application of structural welding principles derived from LST experience. These structures must withstand hurricane-force winds, waves exceeding 60 feet, and the constant dynamic loading of ocean swells. The critical joints, where platform legs meet the deck structure, where riser pipes connect to wellheads, use welding specifications that emphasize toughness and shock resistance over pure strength. Engineers designing these platforms in the 1970s and 80s explicitly referenced naval ship welding standards when developing their specifications. They needed joints that could survive sudden impacts from supply vessels, dropped equipment, or structural failures in adjacent components. The multi-pass technique with thermal cycling provided exactly that characteristic, the ability to absorb energy and redistribute stress rather than fracturing catastrophically. The Piper Alpha disaster in 1988, where an offshore platform in the North Sea exploded and killed 167 workers, led to comprehensive review of welding standards throughout the offshore industry. Investigators found that while the initial explosion resulted from a gas leak, the catastrophic structural collapse that killed most workers involved weld failures that propagated through the platform's framework. Post-disaster, analysis revealed that some critical welds had been made using rapid single-pass techniques to save construction time. Those welds failed under shock loading from the explosion, allowing fire and structural damage to spread uncontrolled. The offshore industry responded by mandating multi-pass welding for all critical structural connections, requirements that remain in force today across every offshore platform worldwide. Pipeline construction adopted similar standards. High-pressure pipelines carrying oil, natural gas, or other materials face unique stresses from internal pressure, ground movement, temperature variations, and potential impact damage. Weld failures in pipelines can cause environmental disasters, economic losses, and deaths. Modern pipeline welding specifications require multiple passes, controlled cooling rates, and extensive non-destructive testing, all principles derived from understanding how welds behave under stress. The Trans-Alaska Pipeline, completed in 1977, used welding specifications developed specifically to handle Arctic temperature extremes and seismic activity. Engineers studied naval ship welding standards, offshore platform requirements, and World War II LST failure analysis when developing their procedures. The pipeline has operated for over 45 years, surviving multiple earthquakes and extreme weather events because its welds were designed to flex and absorb stress rather than fracture. Bridge construction shows the same evolutionary path. Modern suspension bridges, cable-stayed bridges, and arch bridges use welded connections throughout their structures. The joints must survive wind loading, traffic vibration, temperature cycling, and occasional earthquake forces. Weld specifications for these structures explicitly incorporate thermal management and multi-pass techniques. The Tacoma Narrows Bridge, which famously collapsed in 1940 in part due to inadequate understanding of dynamic loading, was rebuilt with welding specifications emphasizing ductility and toughness. Engineers designing the replacement bridge in the 1940s consulted with naval architects about welding practices for structures subjected to oscillating loads. The connection between ship construction and bridge design was explicit and documented. By the 1960s, structural engineers took for granted that critical welds required multiple passes with controlled thermal cycles. The principle had become so thoroughly integrated into standard practice that few engineers knew its origins. Textbooks taught the technique without mentioning LSTs, mine damage, or a Pittsburgh inspector's observations. It was simply how proper welding was done. The space program inherited these principles when engineers began designing welded structures for rockets and spacecraft. The Saturn V rocket, which carried Apollo missions to the Moon, used welded aluminum construction throughout its massive fuel tanks. Those welds had to survive extreme temperature differentials, from cryogenic fuel at -260 degrees Fahrenheit to aerodynamic heating during launch. NASA welding specifications for the Saturn V explicitly required multiple passes, even though aluminum welding uses different techniques than steel. The underlying principle remained constant. Proper thermal management during welding creates joints that survive shock loading and thermal stress. Engineers who developed those specifications had learned their welding metallurgy from textbooks and standards derived from World War II naval construction experience. The International Space Station, assembled in orbit beginning in 1998, uses welded connections throughout its structure. While much of the assembly occurred in space using mechanical fasteners, critical pressure vessel welds were made on Earth using specifications that trace their lineage through decades of welding evolution back to fundamental principles established in wartime shipyards. Modern automobile manufacturing uses welding extensively, though the techniques differ significantly from ship or structural welding. But the principle of thermal management, controlling how metal heats and cools during joining, appears throughout automotive welding specifications. Resistant spot welding, the primary technique for car body assembly, carefully controls current, pressure, and cooling rates to create welds with specific strength and ductility characteristics. Engineers developing these specifications in the 1950s and 60s drew on welding metallurgy knowledge that had been systematically developed through analyzing why some welds survived stress while others failed. That knowledge base included LST combat experience, Liberty ship failures, and countless other examples of welds tested to destruction under real-world conditions. The nuclear power industry adopted perhaps the most rigorous welding standards of any field. Pressure vessels for nuclear reactors must contain radioactive materials under extreme temperature and pressure for decades without failure. The welds in these vessels undergo more inspection and testing than any other industrial application. But the fundamental procedures, multiple passes, controlled cooling, emphasis on toughness over pure strength, come directly from principles established in less exotic applications. The American Society of Mechanical Engineers Boiler and Pressure Vessel Code, which governs nuclear reactor construction, includes welding specifications that nuclear engineers in the 1950s consciously based on the best practices from naval ship construction, offshore platforms, and heavy industrial welding. The chain of influence runs directly from combat experience to civilian nuclear power. Hendrix's observation about fusion line failures appears in modern welding textbooks as an example of incomplete fusion, a fundamental defect that proper technique prevents. Students learn to identify it, understand its causes, and know the correct procedures to avoid it. Few of those students know that this understanding cost thousands of lives to develop, or that it began with one man examining damaged ship hulls in a Pittsburgh shipyard. The technique's ultimate validation came not from any single dramatic event, but from its complete integration into standard practice. When something becomes universal, when every practitioner learns it as fundamental methodology, when failure to use it would be considered professional malpractice, that technique has achieved the highest form of success. It's no longer innovative. It's simply correct. Modern welding certification programs worldwide, whether American Welding Society, European Welding Federation, or Japanese industrial standards, All require demonstrated competency in multipass welding with proper thermal management. A welder who can't execute these techniques correctly cannot become certified. The knowledge has been encoded into professional standards so thoroughly that its origins have been forgotten. Lieutenant Commander Morrison's combat reports, filed in National Archives in boxes of World War II action reports, were declassified in 1972. Researchers occasionally encountered them while studying Pacific War amphibious operations. The reports seemed unremarkable, routine descriptions of mine damage and repairs. Nobody connected them to the global revolution in welding practice that they'd helped initiate. Hendrix's technical report from September 1944 exists in the National Archives' Bureau of Ships Records. The document is publicly available to any researcher who knows to look for it. In 75 years since its submission, it has been requested exactly 3 times. Twice by graduate students researching LST construction history, once by a welding engineer writing a historical article for an industry journal. The article, published in the American Welding Society's Welding Journal in 1998, was titled Evolution of Multipass Welding Techniques in Naval Construction. It traced the development of modern welding specifications through various milestones, including Liberty ship failures, LST mine damage analysis, and post-war metallurgical research. Hendrix was mentioned in one paragraph, his report cited as an example of field observation leading to technical innovation. The article generated no particular attention. It was solid historical research published in a technical journal, read by perhaps 2,000 welding engineers and researchers. Nobody contacted Hendrix's surviving family. Nobody suggested he deserved recognition. The article simply documented that a Pittsburgh shipyard inspector had identified a problem and proposed a solution that eventually became standard practice. That might be the most fitting memorial. Not a plaque, not a medal, not a Wikipedia article, but the simple fact that every welder in the world now learns and uses principles that Hendrix observed. The technique's very invisibility through ubiquity represents its ultimate triumph. It's not Hendrix's method anymore. It's just how welding is done. In 2024, the United States Navy commissioned its newest San Antonio-class amphibious transport dock, USS Harrisburg. The ship's welding specifications run to over 300 pages of technical requirements, covering everything from electrode composition to non-destructive testing protocols. Buried in those specifications, on page 147, is a requirement that all critical structural welds be executed in a minimum of 3 passes, with interpass temperature maintained between 300 and 450 degrees Fahrenheit. The specification includes no citation, no historical reference, no explanation of why this particular procedure is required. It's simply listed as standard practice, one requirement among thousands that collectively define proper ship construction. A young welder working on the Harrisburg's hull in a shipyard in Pascagoula, Mississippi, followed that specification without knowing its origin, without understanding the combat experience that made it necessary, without realizing that the 3-pass technique she was executing had been tested under the most brutal conditions imaginable. She preheated the base metal with a rosebud torch, verified temperature with an infrared pyrometer, struck her arc, and laid down a root pass with careful attention to penetration and fusion. She waited 15 minutes for proper cooling, checked interpass temperature, then deposited her second pass. Another wait, another temperature check, then the final cap pass, creating a smooth, properly profiled weld that would hold the ship's structure together for its 30-year service life. That weld, and the millions of similar welds in ships, bridges, buildings, pipelines, and countless other structures worldwide, represents Hendrix's legacy. Not fame, not recognition, but the simple fact that the technique works, that it saves lives, and that it has become so fundamental to proper practice that nobody questions it anymore. Up next, you've got 2 more standout stories right on your screen. If this one hits the mark, you won't want to pass these up. Just click and check them out. And don't forget to like, subscribe, and turn on the notification bell so you don't miss any upload from us.